Our next topic of conversation is transforming data. Welcome back, folks. Okay. Today we're talking about effects of transforming data. This is page 3 of our packet on section 2.1 titled Describing Location in a Distribution. How many of you have ever had to convert units of measurement from one, like inches, to another, like miles? Yeah, we've all had to convert things before. The example that I'm going to show to illustrate these ideas is straight out of the text, okay? I think I told you earlier in the year that I'm going to try to always use examples that are not in the text, unless the one in the text I think is so good that I want to use it, okay? Because why do I do that? I want to give you two different varieties of the same type of problem. One we do in class, one you can read in the book. This one is so good, though, I wanted to capture it in class. So, effects of transforming data. If we are adding or subtracting a constant, which means we're adding the same positive number to each the positive number I'm referring to is A. We're adding that or subtracting it to each observation. How does it affect measures of center? Well, you just add it to that. Okay? So if the center of my distribution is 5, and then I say, you know what, I'm going to give everybody some bonus points. And I give everybody +2, then the center of the new distribution is 7. Okay, so if we add a constant to every observation in the distribution, it shifts the center. It also does not change the shape of the distribution or change the measures of spread, IQR, standard deviation. So if I take the distribution of test scores and I calculate a standard deviation, and then I add 5 points on everybody's test score, the standard deviation will be the same. The mean, the center has moved, but the standard deviation is the same. Okay, so how can we transform data? We can add or subtract a constant. What if we multiply or divide by a constant? Okay, if we multiply each observation by the same positive number b, well, the measures of center and spread are multiplied by b. So if the average test score is 25, and I want to multiply that by 4, then the average test score becomes 100. Okay? But look at this one. This is different than the previous one. We multiply measures of center and we multiply measures of spread. So think of it this way. If I have a distribution of scores and then I multiply everybody's score by the same value, if that value is greater than 1, the data is going to be more spread out. If that value is less than 1, the data is going to be clustered closer together. I think it makes sense when you think about it. Okay. If b is less than 0, measures of spread are multiplied by the absolute value of b, and the shape is reflected across the x-axis. A couple quick comments here. Why the absolute value of b? Because standard deviation is a positive calculus. It has to be positive. Okay, measures of spread are positive. Okay, shape is reflected across the vertical axis because if I multiply 5 by -1, it becomes -5. Makes sense, doesn't it? Yeah, I thought so. Okay, I want to look at this example, but first I'm going to give you a moment to read what is asked for and the data that's presented. Go. Okay, so we're given temperature data in degrees Celsius. We have this random formula on the paper, which many of you probably wouldn't have known from memory of how to convert from Celsius to Fahrenheit. Find the mean temperature in degrees Fahrenheit. If the thermostat set point is 50 degrees Fahrenheit, that's a little chilly, would you say that it is accurate? Okay, so for mean temperature, what am I doing to each of the measurements in the formula? I heard from an unnamed student, multiply. That's not all. What else am I doing, Sage? Oh, hey, check that. Yeah. Adding. So we're doing both. We are multiplying by a positive constant, and we are adding a constant. So how does multiplying by a positive constant change the mean? Look up in the gray box. If you multiply by a positive constant, how does it change the mean? Do you ignore it? Do you multiply by it? What do? It's in the gray box! Thank you, student shall be named later. You multiply. So if we have a distribution and we multiply every value in that distribution by a constant, our mean has to be multiplied by that constant. What if we add a value to every observation in the distribution? We also add that to our mean. So the mean temperature in degrees Fahrenheit will be 9/5 times the mean of 8.43 degrees Celsius plus 32. 9/5 times 8.43 plus 32. And that will give you a temperature of 47.2 degrees. That is the mean temperature in degrees Fahrenheit. Is our thermostat good, bad? What do you think? Perfect. The set point is 50. It's almost there. Okay, I would say this. The mean temperature of 47.2 degrees is almost 3 degrees Fahrenheit below the set point. It's pretty good, but could be better. We also have to think about the application. Okay, the application is heating it doesn't say this here, but it's probably heating a home. Okay, in fact, if you look in your textbook, they were heating a cabin in the winter that they weren't using. So they just don't want the pipes to freeze. That's why it's set at 50 and not 70, more like room temperature. They don't want the pipes to freeze. So plus or minus 3 degrees in that setting, not a big deal, right? But what if you're trying to control somebody's body temperature? Plus or minus 3 degrees is a problem. Could be the difference between life and death. So the relative quantity there of plus or minus 3 degrees depends on the application. If we're talking about heating a home, not a big deal. It's just we're talking about our personal comfort. If we're trying to save somebody's life, plus or minus 3 degrees could be a big deal. Okay. Calculate the standard deviation of the temperature readings in degrees Fahrenheit. Interpret this value in context. So 2 parts to this question. I'm asked to calculate the standard deviation. What I need is help from you. We've already been told that the formula to convert from Celsius to Fahrenheit involves multiplication by a constant and addition of a constant. How does multiplication and addition of constants affect the spread? Look to the gray box. So the standard deviation, and I'll put S sub F, which represents Fahrenheit. Okay? The standard deviation is going to be affected by the multiplication, but not by the addition. Because multiplication affects measures of spread, but addition does not, according to the gray box. Okay, so that means the standard deviation in Fahrenheit is going to be 9/5 times the standard deviation in Celsius plus 0, because that addition of a constant doesn't do anything to the spread. So we have 9/5 times, scroll up, standard deviation is 2.27 degrees Celsius. And when I grip and rip it on my calculator, I get 4.09 degrees Fahrenheit. What I want you to do now is think about that value in the context of the problem. What does standard deviation represent? This value represents the typical distance from the mean. Just want to make a quick note here. Note. Adding is one word, not two. Adding 32 degrees Fahrenheit to each observation does not. Think of it this way. If I have a group of observations, okay, and I add the same amount to each observation, they all shift the same amount. Therefore, the spread is the same. Okay. The 93rd percentile of the temperature readings was 12 degrees centigrade. Do you call it centigrade anymore, or is it Celsius? I don't remember. Celsius. Centigrade is also used sometimes. Some of you are packing up. I don't know why. We have 6 minutes to go. The 93rd percentile of the temperature readings. Your time may vary. The 93rd percentile of the temperature readings was 12 degrees Celsius. What is the 93rd percentile temperature in degrees Fahrenheit? How on earth are we going to do this? Remember, multiplying by a constant and adding a constant does not affect the observation's location in the distribution. So, 12 degrees centigrade converted to Fahrenheit is equal to 53.6 degrees. And folks, that's a straight conversion. By transforming from Celsius to Fahrenheit, we do not affect the observation's position in the distribution.